In 1900, the laws of nature seemed predictable. Classical physics worked beautifully, but there was one nagging problem. According to the best theories of the time, any hot object, a candle flame, a glowing piece of metal, even a star, could radiate more and more energy at higher and higher frequencies. The equation said the energy would keep rising without limit. Nothing in nature behaves that way. If it did, every warm object would instantly vaporize itself. Yet the math insisted this must be true. Physicists trusted their equations, but the equations were betraying them. It was a catastrophic contradiction between theory and experiment. The solution would come from a conservative German physicist. He introduced a strange assumption that energy is emitted in tiny, discrete packets. He later called it an act of desperation, a mathematical trick to make the numbers work. He had no idea he had just opened the door to an entirely new layer of reality, the quantum world. At the turn of the 20th century, physicists faced a misleading simple question. Why does a hot object called a blackbody glow? This didn't feel like a mystery. Throughout the 1800s, glowing heat was everywhere. In blacksmith forges, in furnaces, candles, and even stars. It was so ordinary that no one questioned it. The assumption seemed airtight. Hot things glow because heat makes things vibrate, and vibrating things emit light. Nothing seemed strange about it. It was too familiar to look suspicious. By the late 1800s, the rapidly growing electric lighting industry needed to understand how the heated filaments inside the incandescent bulbs produced light. Questions about efficiency, heat-to-light conversion, and glow color that ultimately pushed physicists towards what became known as the blackbody radiation problem. Heating an object speeds up the vibrations of its charged particles, and those vibrations create light, but at specific frequencies. Light frequency is directly tied to vibration speed. Slow vibrations produce low-frequency light like infrared or red light. Medium vibrations produce visible light, such as orange, yellow, or white light. Very fast vibrations produce high-frequency light, such as blue or ultraviolet light. The best theories they had at the time, what we now call classical physics, offered an answer. If you keep heating an object, the vibrations get faster, so classical physics predicted it should emit tons of high-frequency light. But that prediction was wrong. According to the classical model, as an object heats up, it should give off increasingly stronger, high-frequency light. The math predicted that this energy would rise without limit in the ultraviolet part of the electromagnetic spectrum. Add it all together and the total energy becomes infinite. That was obviously not happening. Warm objects do not blast the world with deadly ultraviolet radiation. They glow red, orange, and yellow, not infinite ultraviolet light. This would later earn a dramatic name, the ultraviolet catastrophe. This was a catastrophe in the sense that it was an utter failure of the old theory to match the real world. It was a mismatch. Physics theory said a warm object should emit infinite ultraviolet light, but reality said warm objects emit almost no ultraviolet light. Ultraviolet light requires way more energy. It was a fundamental breakdown of the physics that they trusted. And this meant that something, somewhere, was deeply wrong. So enter Max Planck, a German physicist who deeply believed in the laws of thermodynamics, the branch of physics that describes how heat and energy behave. But a problem pushed him into unfamiliar territory, that of blackbody radiation. Blackbody radiation is the thermal glow that any object gives off purely because it has a temperature. It doesn't come from chemistry, electricity, or special materials, just heat. In October 1900, he introduced a formula that matched experimental data perfectly. Then he spent the next few months trying to justify it. In December 1900, he made a startling assumption. What if energy could not be exchanged continuously? What if energy came only in discrete amounts? proportional to the frequency of the light. He called these discrete units energy elements. Later, they would be known as quanta. Planck did not present this as a revolution. He didn't realize the implications of his own formula. The true revolution only became clear years later, when other physicists looked back on his work. He considered it a recognized assumption, a mathematical device needed to make the theory work. He would later describe it as an act of desperation. Planck introduced energy quanta as a mathematical fix to a problem. He did not yet realize he had accidentally launched the field of quantum physics. So Planck's desperate guess worked perfectly. By assuming that energy came in these discrete packets, the ultraviolet catastrophe simply vanished. His idea was basically this: energy could only be exchanged in tiny packets, not in smooth, continuous amounts. And here's the key: the hotter an object is, the more energy it has. The more energy it has, the bigger the light packets it can produce. Bigger packets equals higher frequency colors. So warm objects can only afford small packets of energy, so they glow red or orange. The hotter an object is, the more likely it is to produce higher frequency, higher energy packets, so they glow white. Extremely hot objects like stars can afford even bigger energy packets, so they emit blue and ultraviolet light. This was the first time anyone realized that temperature controls glow color, because energy comes in chunks. His idea explained why warm objects don't give off dangerous amounts of ultraviolet light, even though older theories predicted they should. He introduced a new fundamental constant, h, to define the size of these energy packets, which we now call Planck's constant. Einstein later recognized that Planck's constant would become one of the most fundamental constants in physics. Max Planck may have been a reluctant revolutionary, but he had just given the next generation of physicists the key to an entirely new universe. Just a few years later, a young Albert Einstein took the idea of quanta seriously, using it to prove that these energy packets were in fact real. From there, this one idea led to our understanding of atoms, the invention of the laser, and the chips that power our entire digital world. So the next time you see a hot burner on a stove glowing red, remember the cautious genius who, in a desperate attempt to fix one physics problem, accidentally discovered a whole new reality. In the next video of this Quantum Mind series, we'll look at Albert Einstein, his unlikely journey, and his ideas that transformed modern physics. Until next time, remember, stay curious and keep exploring. Thanks for watching.